I think we can get started. Welcome back, everyone. I hope you all had a restful holiday, weren't shoveling snow the whole time. For today's class, we're going to be running through section 2.3. This one's kind of longer, so I'm not certain if we'll complete it today. We're not going to try to race through the documents. We'll take the normal amount of time, however long these ones are. But this one's a bigger section that leads right off of section 2.2. Think of 2.2 as we're wondering what happens to the function if you're going to the left forever, negative infinity, or when you're going to the right forever, positive infinity. But that leaves everything that happens in the middle, all the local behavior, completely undetermined. And that's what this is about. When we're going to finite numbers, we're looking for the fine details of what happens to this function, aside from going off to the left or off to the right. So that's what we'll be working on. It segues pretty well off section 2.2, so it kind of feels like we're doing just the same kind of stuff. And the other new thing for the announcement is we have our very first quiz posted. So here's quiz number 1. The due date for this is going to be a week away from today. And pretty much my style will be, I'll have these posted when we come to Wednesday's class. And the due date will always be 1 week right after. So you'll have an opportunity to get some questions asked on the quiz and answered, those kinds of things. But one thing I want to mention is that for all the quizzes are a participation credit. So officially, that's the whole purpose of the quiz. It's a way for you to engage with me, do some math problems, get some feedback, maybe see some corrections that have to be done, all that kind of stuff you'd want to do before actually doing an exam. That way you're going to have a really good idea of how the exams work. Other thing to mention is, for all of my quizzes, I wouldn't bother you with a fluff problem. These are all, let's say it this way, all quizzes contains typical exam problems. And I've taught this course for now a number of semesters. Sometimes the way I do these quizzes is I go to an old exam a couple semesters in the past, so that's one we're not reusing for sure. And I just take that exam, find out which questions would format great as a good quiz question. So you can think of all of your quizzes as, sure, it's a participation credit. It's a way to see if you're doing the right amount of work or the right kind of techniques on each problem. But you're also studying for every one of your exams on every single quiz that you work on. Those are all the typical questions I would ask on an exam. So you're getting feedback on real exam questions, essentially. And maybe the last thing to mention here, when it comes to quizzes, every one of them is going to be worth 10 points. So that's just the total for every one. And 5 points out of 10 is turning the quiz in on time. So just doing the quiz, irregardless of the correctness of it, that's half the credit. You participated, so you'll get 5 points out of 10 for sure. Then the remaining 5 points, that's just based off correctness. So let's just say it this way, 5 points out of 10 is for correctness. I'll give a lot of feedback on each one of those quizzes. So if there's a simple mistake, I'll mention it on your quiz. You might lose a half a point if it's something really small numerically. If it has something to do about the calculus, if that negative sign was an important feature of the actual calculus in the problem, it might be worth 1 point or 2 points for a simple mistake, that kind of stuff. And really just the general advice for writing out your quizzes. The answer itself might not be worth a lot of the 5 points, maybe just 1 point for the actual answer. But all the steps you do, if they're correct, getting to that answer, that's where all the rest of the credit is. But maybe said a different way, a correct answer with completely incorrect work getting there, you might lose 4 points out of 5. But an incorrect answer with all of the correct work getting to that incorrect answer, you might get 4.5 points out of 5 if it's just was a simple mistake, but your whole process is what was correct. The logic of, or the step-by-step work. So that's how each one of these quizzes will go down. And that's a lot of comments, so let's put this right here in section 2.3. We'll make it our first page. And if there's ever a comment on the Moodle website that I feel like we should record that somehow, other than a YouTube video, you might see it on the notes, and then the notes will begin officially right down here. Okay, so that's our advice on quizzes. What this doesn't tell us so far is how to do the quiz, so let's clear all this out. But first, any questions or comments at the moment? Okay, let me clear off this annotate stuff. Now, to actually do your quiz, well, it's always going to be at the very bottom of the week because it's like the last thing that we'll worry about. We'll have the due date. Click on the quiz itself, and it'll just give you a PDF. Click on that, and here's your quiz. It's a problem that'll be typical from the ones that we did. And again, this was a question here and here, 1 and 2, that was really asked on a real exam in the past. So let's do it January 24th. And you can do this in a number of ways. Some people might print this out. That's why I have like the name, quiz number, and such. You don't have to print them out. You might just grab ordinary notebook paper, solve your limit here, and this limit on paper, then just take a screenshot, send it to my email, or drop it in class on the desk on the due date, and that'd be a great way to do it. If you like, you can print it out, work on it pen and pencil, or you can work on it completely digitally. Just mark up your work here. And I'll give you feedback digitally. So the way you do your quiz in a way that you'd like to get it back. If you want a hard copy back, you have to submit a hard copy. If you want a digital copy back, then just send me a digital one and I'll email it right back to you. So after you complete your quiz, again, you can turn it into class physically, or just take your completed quiz and email it to me. And that's how all the quizzes will go in this class. Well, any questions at all, folks, about this quiz here? Okay, let's close this off. And that's again how the quizzes are going to work. I try to make them decent questions that summarizes what we did the prior week, or maybe even the Monday before the Wednesday this is posted. And they will always be very worthwhile questions, helpful for studying for the exams. Well, that's pretty much all of our announcements for the moment. I want to go into WebAssign and talk about a couple things in there first, but any questions, comments, or concerns so far, folks? Okay, we're still just kind of starting the class. This is only our 3rd class meeting, and we're 7 minutes into the announcements. Usually we'll get right into the lesson a little bit sooner, but we're only just getting started. So let me minimize a couple of these windows a bit. And back in WebAssign, here's what WebAssign looks like now that one section has gone past due. I set the time on these to 7 p.m. Actually, WebAssign just does that by default. And what you would do if an assignment does go past due is you find them right here, past assignments. Let me move that window for just a moment. Click on past assignments, and it says, let's see here, for past assignments, section 2.2 went past due on my end. Click on this right here to request an extension. And here you have a lot of freedom. This is a good time to mention that the due dates are important in this class. They're more important for quizzes where there's a 5-point contribution for getting the quiz in on time to begin with. But as far as the sections go here, the due dates are more about pacing than anything else. If you're completing each one of these sections by the due date, you're in great shape for keeping up with the course. But something goes past due, click on again, request an extension down here. And I'm not too worried about the kind of stuff you put here. Only requirement is you have to put in a date that's before, let's see, the end day of the class, which would be April 29th. Some people give it a 1-day extension. That's completely up to you. I'd recommend going a full week. Makes sense. Down here, you can change the time if you like. Down here, it's asking for a reason, but I'm not going to badger you about your personal life. I get it. I have lots of commitments myself outside of this class. Life gets crazy. You can just say life got crazy, or just leave it completely blank. If there is a reason that you think I should know, but only as your instructor, you could put that information down there for why you request an extension. But I'm not going to try to ever badger you over that. You can request an extension as many times as you like in this class on as many different sections as you would like. So once you click on submit, it says request was submitted, and nothing seems to happen for a minute. So you have to be a little bit strategic on when you do request an extension, because I have to come back over here on this side of the system. I'll get an email notification on Gmail, so that helps me out as well. And I come up here, click on this, and I pretty much just put in the extensions manually. And I'm never going to deny an extension. If something went wrong, I might have just misclicked. Maybe I'm tired or something. I'll always just click on grant. I'll match up the due date that you asked and send it off. So you'll get an email after that happens that your section is open. Let's refresh this and see what it looks like. There'll be nothing here. It's gone from the past assignments. Go back to current assignments. Some of these might get out of order depending on the date. If you requested, say, like January 30, then you'll see 2.3 ahead of 2.2. So they might get a little bit misordered after the extension. But that's pretty much how it works. Any questions about it, folks? Okay, so if you have assignment go past due, you'll lose points for that section, but just request an extension, get back in there, keep on working it, and you can get back to 100%. I'm not going to penalize you for something going past due. Only requirement is to get back in and finish the problems. So that's my thing I want to mention with WebAssign. Were there any questions or comments or things you want to share about WebAssign? Has been working or not working, anything like that? Yeah, go ahead. Awesome, glad to hear that. I should mention that WebAssign as a system from Cengage, it hasn't been the most reliable system. There's been weird errors. They're all like very specific, like one user for one semester, they couldn't get their textbook even though they clearly paid for it. So if anything is just weird or awful like that, email me, contact tech support, we'll get it sorted out one way or another. But definitely let me know sooner than later so we can get it figured out. Again, last thing about extensions, because I have to come in and put in those extensions, I'm usually checking them very, very early in the morning, like around 7 a.m., maybe again around 11. But around this time, I'm kind of locked out. Office hours go 4 to 5. I'll try to get some in, but I'm running to this class because I have a class 5:30 to 6:45. Then ours goes 7 to 8:15. Right around 8:15, I'm pretty much just packing it up and going to bed at that point. So I usually try to do this work where I can make mistakes in the morning and that kind of stuff. Well, that's how extensions work. Any other questions so far, folks, about any of those announcements? Okay, maybe one last thing to mention. This class is really kind of weird in a certain sense. It's a hybrid class with people in person, people coming in online. And so one thing to mention is, on my end, this is not a really well set up classroom for Zoom. Ideally, what I would want is something like, say, a whole separate monitor so I can open this up and interact better with people in the class. Instead, I'm going to be using pretty much this participation window right here. There's different things you can do. You can respond to me by doing things like, oh, there's a thumbs up key. I can't find it. You can do different kinds of things in here to interact with the class. So probably the best ways to interact are definitely over voice if you have a microphone and your room is not too busy. But I'll try to be very responsive on chat as well. So you can always participate in chat. Keep in mind, if you look at the chat, you're going to see a lot of stuff from the last class. So ignore everything past like the 6:45 p.m. you see right here. Well, with those announcements, let's get started. Let me move this over here. I'll try to keep one of these open and the participation window open to interact with folks coming in over Zoom. And we're in section 2.3, so here's what the notes look like. First, a message from Moodle about quizzes, and then here are the actual definitions, finally. So we're taking limits, but this time the major thing that's changed is we're taking the limit as x approaches a finite number. We'll just call it generically a. So we're not going off to positive nor negative infinity. If we go off to a, and it results in a value of L, then what this is saying is we have the limit of f of x as x approaches a equals L, meaning the closer and closer the x gets to that number a, the closer and closer f of x will get to L. And you can make f of x as close to L as you would like, arbitrarily close, by making x sufficiently close to A on either side. It has to be approaching both sides at once. But we don't care about what happens at A right here. So right at A, the function value is irrelevant to the limit. That's really kind of weird. So let's focus on this part right here. When we do these kinds of limits, I think this is about the most confusing part that we have to resolve when we go through the notes. That's why we're doing this visually to start off with these problems. And then in section 2.4, we're doing the same things, but we'll be using the limit laws. So here's our function f. It's this entire blue curve, and it has some weird features. It comes down linearly, and then right here is a discontinuity. The open circle says there is no function value by this red dot. The function value drops way down to this location. So we're going to calculate f of 1, and the limit as x tends to 1 of f of x. Let's start with the familiar. If you're calculating f of 1, it would go like this. We take the input of 1, find it on the x-axis, so we're right here. Then we either go up or down until we hit the graph, but hitting the graph means we're not going to hit anything right here. We pass right through. We hit this location. Then the output is that number right there. So f of 1 turns into 1. And if you like arrows, here's all that's happening with f of 1. We start at 1, hit the point on the graph, and we outputted a 1. So that's what f of 1 is doing altogether, visually. What does that make sense to folks at the moment? Okay, now here's the confusing thing out of nowhere. The limit as x tends to 1, this one is a lot more confusing than in the prior section 2.2. Lim x tends towards 1 of f of x. Now, recall, we don't care about what happens at A. The A in this problem is the 1. Because it's irrelevant what happens when x tends to 1, this function value, it's really here just to kind of throw us off, see what we're going to do with this problem. But here's what you could do. Because right at 1 is irrelevant, you could really do this. Blow it out of the problem, put in a line segment, put in a vertical strip, because nothing matters right here. That's maybe too wide. Let's put in like this. So just imagine there's nothing there. If you compute the limit this way, this is actually easier. Put blinders on it. Kind of a weird strategy for sure. But now let's look at what happens to this thing. We want to say it's equal to some number as x gets closer and closer to 1 this time. But we have to approach it from either side. Let's bring 1 back just so we can see it. So we're going to approach it on either side. And as we come in from the left, the function values, well, right here, they're at height 3, and they're decreasing more and more until we get to around 2. It stops decreasing, but if we come in from the right-hand side, it comes in, decreases, gets lower and lower, but it gets lower and lower approaching 2 specifically. That means the limit of this function is 2. Does that make sense to folks? Okay, so this value of 2, it's just the output that the blue curve is approaching arbitrarily close to as you're getting closer and closer to 1. But again, some people like arrows. Let's throw arrows on this thing. If you zoom really, really close on this, taking the limit as x tends towards 1 just means you have to be really close to this 1. Say you're right around here. The function output would be at this height. That's just above 2.5. So get closer to 1. Now right here, function value would be at about height, say 2.3 or something. But we need to approach 1 even closer. Now it's getting closer to 2 itself. We could zoom in more and more and more and just repeat this. Whatever we do, we're just approaching 2 more and more closely. That's if we're approaching to the left. If we're approaching from the right, well, it's the same kind of idea. Let's actually take off this whole black bar this time. If we're approaching from the right, here's what the limiting process looks like. Here we have a 2.5. Let me put the red dot by 1. That's where we're heading towards. Next, we're decreasing to about a 2.3. Here, maybe it's a 2.2. Down here, maybe a 2.1 and so on. And that's just for values that are right around here for the 2.1. Get closer and closer to 1, and we can get even closer to 2. But if we zoom out to the whole picture, to me, this is the thing that makes all of this pretty tricky. F of 1 gave us this value, but the actual limiting process gives us a value of 2 instead. The function value and the value of the limit don't have to agree. And places where they start to disagree is where you see this, a discontinuity. Over chat, we have a question. Can you get infinitely close to 2 without actually touching it? So rounding gets you to 2. So that's essentially kind of right, except we're not even thinking about rounding. We're just saying, if you want to get, say, to a 1.9999 with 29s, just find the right value that's close enough to 1 to get us to that location. So the rounding would be more like we're outputting the 1 because we put in directly a 1. Does that kind of make sense with that question there? Awesome, thanks for asking that. We're spending a lot of time on this one because, again, this is a weird process with limiting. That's what makes calculus kind of hard starting out. Once we get to the next chapter, it's not all this kind of stuff. But the downside of calculus is that every single interesting object in calculus, there's 3 big ones: continuity, differentiability, and integrability. That's a harder word. All of it's defined through these things. The limits are the underlying machinery that makes calculus work. They are weird, so we're studying it with graphs first to get the feel for it. Well, other questions or comments, folks, on looking at this one? Okay, because this is such a tricky process, let's look at it again in a slightly different format. Here's our example 2. It says compute the limit of the functions. So now we're looking at 3 different functions this time. As x tends towards 1. Let's move the windows just a bit over here. So 3 different functions. First function is x squared minus 1 divided by x minus 1, and it plots this way. This is a highly accurate plot, but if you put this in a graphing calculator, let me show you what it actually looks like. So we're plotting this function. Desmos, it'll just be that graphing calculator that's easiest to show in class. Let's type f of x equals x squared minus 1 divided by x minus 1. Now here's the plot they produced in blue. Here's the plot Desmos would produce, or your TI-84 graphing calculator, or those kinds of things would produce. They don't look the same. There's a problem at 1 here, but here it looks like it's smooth and continuous. But the more you look at this, the more you'll notice that there is a problem. Right here at 1, let me see if I can get that to stay. You'll see an open circle and it says undefined. So there is truly a problem here. The way these graphs were produced is they just did function values and they connected the dots. They connected through 0, and that's actually hiding information about this graph. There's a real and honest discontinuity there. But looking at this thing, there's no weird issue like what we dealt with right here. This is a friendlier limit. We're taking the limit on this one as x tends towards 1, so let's write it out. Limit, that's the operator. That's the function that takes a direction. X goes to 1, and it also takes an entire function, f of x. And here's our f of x function right here. As we tend towards 1, anyone see what the output should be, the actual limiting value? Sorry, say again. It wouldn't be 1 on this one.
Is it 2?
It would be 2, good call. So this one again is kind of weird. It has an open circle here, but The limit doesn't come out as 2, because if you get close to 1, here's pretty close. The values are getting closer and closer to 2. And that has to happen on either side of 1. So if I'm on this side, say even closer, about as close as I can do, I don't have a perfectly steady hand. We'll come out here, and now we're even closer to 2. So it looks like the function values are heading towards 2 on this one. The limit itself is 2. But notice also, let's put this in orange, f of 1 is undefined. So even if the function is not defined at a specific value, its limit can still exist. And we saw that on Desmos 2 different ways. Right at 1, function value is undefined. There's a true hole right here. But the limit itself does exist because the curve gets arbitrarily close to 2 as x gets close to 1, even though there's a hole here, a missing value. So that's one limit down. And when we go to do this one, we're changing from an ordinary function to a piecewise defined function. These are kind of awkward to work with, but graphically, this is what it looks like. F of 1 was undefined before because of that hole, but we defined it with this g of x function. We're calling it g, it's a brand new function, and g of 1, well, it says if x is 1, g of 1 is 1, and that's just what happened to that point right there. But the thing that's tricky about graph number 2 is the fact that we redefined it and put in a function value is irrelevant. The graph is still heading towards 2 from the left, and from the right, the height is approaching 2. So on this one, the limit as x tends towards 1 of g of x is also 2. No change at all in this limit. Does that make sense to folks on our graph here for g of x? Okay, now something happened which is really weird. Well, let's first mention this one is a discontinuity. And the type of discontinuity this one is called removable. Over here, same one. It's another discontinuity. There's a hole in the graph, and it's removable. But this one is continuous. We've removed the discontinuity by defining the function right here to have the function value of 2. So this one is continuous. So if we look at this h of x function, it's just x plus 1. That means if we plug inside 1 here, h of 1, that's just a 1 plus 1 giving us a 2. But we could have done it through the graph as well. And like before, the limiting process, if we take the limit as x tends towards 1 of h of x, well, nothing too special happens. We'll get closer and closer to 2. We don't care about what happens at 1, even if it's defined. Even if it's defined in a continuous way, we still don't care about what happens at 1. What we care about is on either side of 1, this one down here, the height of the curve is approaching 2 as we get closer and closer to 1. That means the limit on this one, also 2. Kind of strange in a certain sense. Well, we did it, folks. That's, in my opinion, 3 pretty tricky type of problems. It was all about the limits. And the stuff I put here in orange is just extra notes or extra information. Things you wouldn't have had to put down to get full credit if this was a real exam question. Well, any other questions so far, folks, on the conclusion for this problem? Okay, let me add just one extra detail to what's happening here. We have strange things happening with this f of x function and the h of x function. They look essentially just the same function, and in fact, their limits are the same. But if we look at f of x, that numerator is special. That can factor as a x plus 1 times a x minus 1. The denominator was still at x minus 1. And so we can do the ordinary algebraic thing to this, do a cancellation this way, and write that it's equal to x plus 1, which is equal to, well, that's the h of x function. So algebraically, this is what everyone would pretty much write in an algebra class. F of x, through some algebraic work right here, resolves to h of x. But there's actual y. If we look at the graph, this is f of x, that's h of x. They are not the same function. There's difference exactly in one spot when x is 1. So the way we resolve this, even though we don't write it in, it's an important thought to make. That equality right there came with real conditions that we gloss over. But the conditions are that this is true if and only if x is not equal to 1. So we're not too worried about the actual value of 1 itself right here. The functions do agree. Well, the major purpose with this example number 2 here was just to see what happens when there's an undefined value, when it's defined, but defined in a weird way, and when it's defined in a more natural way. The limiting process didn't care at all about that point at x equals 1. On every single one of these problems, you could have done this once again. Just completely ignore what happens at x equals 1. And all of these limits are still correct. You're heading towards 2, either way you look at it. Well, we did it, folks. That's our discussion on limits. But the trick with, or the trouble with limits sometimes is there are a lot of different kinds of limits. But before we go to the next type, let's maybe try, oh, no, let's go to the next type, it turns out. Forgot I must have had a different problem I was anticipating. Here's the next type of limits that we're going to take a look at. So sometimes our functions have discontinuities like we've been mentioning. And so far the discontinuities weren't major. It was just like a point missing in a location. We called them removable. But this discontinuity we're about to put in is much more substantial. Once I fix this, let's go back to original width. We're going to write a one function for this part of the definition and this part down below. We're heading towards a, but we'll put in a specific value for a. Let's make our a in this problem be, how about 3? That's easy to plot. So we'll go 1, 2, 3. And the graph is going to have a really big problem right at 3. So first, let's put in some values here. 1 through 4. Let's say at 3, we're defined, and we take out the value 4. So f of 3 is going to be equal to 4 by that point there. Now here's where it starts to have some problems. Let's put an open circle at a height of 1, an open circle at a height of 2, and the curve is going to go like this. We'll shoot up and to the right in that direction, and it comes in and approaches that curve right there. It exits at the height of 2, and let's just make it go down like that. I'm not too worried about what happens on the edges, but just because we can, let's describe it. On this far left, just as a review problem, the limit as x tends towards negative infinity of f of x would be positive infinity, because we're going up and to the, we're going left and upwards as we head towards the left. On this one, no asymptote here, we're heading towards negative infinity. So we might write lim x tends towards positive infinity, because we're moving to the far right, of f of x equals negative infinity, because now it's shooting down on that end. But what we care about is this local behavior right here. So there's 2 new kinds of limits. And this right here is going to be referred to as a jump discontinuity. It's called a jump this time because it's like the whole curve went from here, it jumped up to this new height and then continued on. You could fix the fact that there's a jump by taking this whole entire curve right here and just walking it down like that. There we go, no discontinuity. Control Z that though. So we have a jump discontinuity there. Now let's take a look at these limits. Notice, again, calculus is very notationally dense. there's a new symbol right here. It's in the position where you would put an exponent. It's in the superscript position. And because it's a negative sign, that means we're approaching x close to a like before, but x is less than a. In other words, we're approaching a from the left if you see that negative sign. But if it comes out to some value L, that means you really are settling down to some height as you came in from the left. Let's write this out. Let's do the left-hand limit. That means we're following this curve in this way, coming in from the left. It would be written in as lim x tends towards a, with a negative sign here to say from the left, of f of x. And this whole thing, well, if we follow the curve, you can really just put your finger on it. It's getting higher and higher and higher. Right around here, it's getting closer to a height of 1. It will never hit the height of 1, but that's the value it's approaching with whatever precision you want. You can get as close to 1 as you would like. And so we'll say this limit emerges as 1 itself, but only if you come in from the left-hand side right here. Oh, I didn't want that one to move. I'll fix this one in a moment here. Okay, well, any questions, folks, on this left-hand limit? Okay, so a good trick here to think about it is, if you see the negative sign, put your finger on the curve to the left of 3 and just start approaching, see what height the curve is approaching itself. Approach that height of 1 right here. But now we can take a different limit. We will go from this with a plus sign. That means we're approaching the limit from the right hand of the curve. And this is the portion we care about. So it'd be written as limit x tends towards a with the plus sign means we're on this edge of the curve, heading in from the right-hand side. We say of f of x. And anyone see what this limit right here ought to look like or come out as? Exactly. We're approaching on the right-hand side, and right around here, it starts to dip down to what I intended to be a height of 2. So imagine that lines up perfectly on this by hand sketch. I'll use a dashed line for a bit of optical illusion. So this one comes out as a 2, but only if we head in from the right. Now, this implies a really interesting question at this stage. The left-hand limit is 1, the right-hand limit is 2, and this one is the double-sided limit. Limit as x tends towards a of f of x. It's a bit of a conundrum, and in mathematics, this is a massive conundrum. We would like our interesting operators or interesting functions or any objects to give us a unique result. The limit is a really interesting operator, but we're using dead-on equality, meaning there should be a unique answer to this. It's either 1 or 2. That's no good to us in mathematics. That's multiple different answers. So what would you say we should say right here if there's more than one potential answer? Let me erase that equality right there. It turns out this is one of the cases where that limit does not exist. So you could write out this way, does not exist. And a common shorthand is DNE, for does not exist. So the only way this limit would have existed is if the left-hand side and the right-hand side limit both agreed. So in other words, if you spotted a jump discontinuity, that limit is just not going to exist. The single-sided limit coming in from the left exclusively or from the right exclusively might exist, but not the double-sided. That's an important enough statement. Let's make that official. Let's start by saying for jump discontinuities, now this is not your ordinary limit. Well, it kind of is, but it's special. It's a double-sided limit. So let's say for jump discontinuities, the double-sided limit does not exist, DNE. Let's point at that one to refer to that as being that double-sided limit. So now we're still doing limits at finite numbers, and we're looking for a finite result. That's the finite number equals L, but we can take a specific direction now. Thank goodness we're only in 2 dimensions. If this was in 3 dimensions, there's more than 2 ways to approach a limiting value. There's infinitely many different directions all of a sudden. But in the plane, with our functions plotted this way, here's our theorem. It says the limit as x tends towards a of f of x equals L, in other words, the limit existed, if and only if the left-hand limit, it's a left-hand because of that negative there, and the right-hand limit all agree. Let's say this in a different way. That statement is true with no provision on the direction for A, if and only if both of the single-sided limits all agree, say the same number. So we had to say does not exist because there was a disagreement here. The limits changed. Well, that's what happens with a jump discontinuity. And because this is kind of a tricky set of problems right here, let's try it all over again on example 3. Before we jump to example 3, were there any last questions or comments on any of these plots that we produced? Okay, let's jump down to that new problem then. And this one's kind of a decent review problem. It's not just single-sided limits. This looks like a graphic I stole from our book, not the best screenshot. I'll try to get a little bit more clear screenshots when I use these things. It says, use the given graph of f. So this is its graph. It comes in 2 pieces. So here's our jump discontinuity. We want to state the value of each quantity if it exists. And if it doesn't, we'll give an explanation. And when you see these instructions on, say, a quiz or a real exam, you could do the same thing that we do here. I try to write out all the notes in a way that this is how we'd expect the work to be done on, say, an exam setting. Let's start off with this one. It says the limit as x tends towards 2, but we're coming in from the left of f of x. Well, if we're coming in towards 2 from the left, here's a strategy that you could use. Right at 2, none of this matters. You could use just another piece of paper, cover it up, or put something over the graphics on your monitor. If you're looking at this on WebAssign, that's probably better than this. Let's use the participation window. That should work for us. So if we're heading towards 2 from the left, that means everything to the right is suddenly irrelevant. Let's put in this just to emphasize that. Anyone see what the value should be then for this limit? Yeah, absolutely. So follow your finger, the height of this curve is settling down towards a height of 3. And the function value itself equals 3, so that's kind of nice. So here, let's put in our limit of 3. Then we're going to change it around. It says next, take the limit as x tends towards 2, but with a plus sign, meaning we're coming in from the right. So let's cover it up. That means everything to the left is irrelevant. It's just there to kind of throw you off. And oh, geez, we kind of would want that scale. Let's use the redacted pen, actually. So imagine there's nothing here, no curve whatsoever. Any volunteers for what this limit should be? How about over Zoom? Anyone in Zoom see the value of this limit here?
Wouldn't it be 1?
Yeah, good call. Thanks, Michael. So this one will come out to a, we're using black on this one, equals 1 altogether. Let's bring back the whole curve. Now, the fact that there's a solid dot here and an open dot here is completely irrelevant to both of these limits. Nothing really matters at what happens to 2. It just matters what happens to the height of the curve as you approach 2. From the right, it comes out to a 1. And from the left, it comes out to a height of 3 instead. So, well, that's 2 limits down. And now here's our next limit, the limit as x tends towards 2. Well, this one is a does not exist. So you can write D and E for does not exist, write it out, or you could say undefined. I would treat that as synonymous with does not exist. This limit value here is truly not defined, but it also says explain why. These are really brief explanations, and you could say there's a jump discontinuity. That always works. If you're doing a double-sided limit, there's no plus or minus next to that 2 by the red dot. That means you can't have this jump discontinuity. So if you say does not exist, jump discontinuity, I would consider that full credit. But you might be thinking of this theorem right here. You could say it doesn't exist because the single-sided limits are different. Let's go with that approach. Theorem 3 does not exist because lim x tends towards 2 from the left of f of x is not equal to, so we're saying the limits disagree. Limit as x tends towards 2 from the right using a plus sign, f of x. So the left-hand limit, the right-hand limit disagreed, and that's enough for us to say does not exist. Well, that's half the work done. Let's go down to row 2. Any questions or comments at the moment?
If they were this, so if it was like 2 for the first one and 2 for the second one, then instead of D and E, would it be also 2 for there?
Exactly, yeah. So if you imagine that this graph wasn't here, if you answer 2, then this one has to now agree, it must be 2, exactly. That's kind of what the theorem is saying up here. If this single-sided limit exists and equals L, so do the other 2. And if and only if, it's just saying the logic goes both ways. If you started with just these 2, the single-sided limit, you conclude this limit exists. But if you start by saying this limit is broken, then one of these is going to have a problem or they're just not going to agree, in other words. Well, let's now try everything on row 2. Row 2 is weird because now we're doing function values. So when we head towards 2, I should probably Control Z some of these before I forget. Sometimes I do forget those kinds of things. And if you notice there's something that was just a comment that looks kind of funny there, just email me and I'll go right back to the notes. But now when we're looking at f of 2, it looks funny because when we headed towards 2 from the left, we got a 3. From the right, we got a 1. The limit at 2 didn't even exist. And now we're asking, well, what about the function value? Anyone see what this should come out as? It would be 3, exactly. Because that's a solid dot there. Input a 2, you pass through the open circle, it's a solid 1, and the output is 3 for that one. Sometimes, and it's strange, the function values can get tricky once we focus so much on limits. So it's good to mix them in. You can kind of expect those to be mixed in here and there. And just because we can, let's take the limit as x tends towards 4. Now this limit is special. It's a double-sided limit. We're not picking a direction. So whatever value we're thinking, it has to match. If you're coming in from the left, looks like we're heading towards 4. And also has to give you the same value as you head in from the right. Heading in from the right, yeah, it looks like we're getting, it goes up, but then back down, a height of 4 once again. So on this one, we would just say 4. But we can tell it exists because it didn't have this feature, the jump discontinuity. If it looks like that, you should expect the limit to exist. Let's maybe put in those descriptions once again. This right here is referred to as a jump. Discontinuity. But this one, that one's a removable discontinuity. I'll sometimes write DISC to refer to discontinuity since that's an awfully long word. We wouldn't want to waste digital ink, I suppose. So as the limit as x tends to 4 of f of x gives us 4, we now want to wonder, what is the value of f of 4? Anyone see what we should write right here? Good call. This one's a little bit odd. There's no dot defined on this graph. So we'll write on this one, undefined. And I noticed my work kind of should put a little bit extra space between these rows, I think. Let's use that as the separator between these different parts of the questions. So it's typical for functions. When something doesn't exist, we say undefined. And it's more typical for limits. When something is undefined, we say does not exist. But those words are interchangeable. It's more of a stylistic choice of how you're saying it, but you're saying the right thing either way. Well, that's our example 3, reviewing some of these limits. Oh, good call. Thanks for mentioning that. I would have lost a point on that one since I did not explain it as well. So let's say here for the explanation, let's say there's no solid dot at x equals 4. Let's make this black. This is an official part of the response here. It's part of the instructions. At x equals 4, there is no point on the graph. And I'll put in parentheses, no solid dot, which would be referring to the point on the graph which is missing. There's just a hole and nothing's been defined. So that one purely undefined. It's called removable because you can remove the discontinuity. By defining the function value in that way, plug the hole and you have continuity. That's the only reason it's called removable. Well, that's our complete story on example 3. Thanks for spotting that missing part of the instructions there. Other questions at the moment?
If that was filled in, it would be 4 then.
Exactly. Filled in right here gives you a value of 4. And say for just another example, filled in right here would give us a value of f of 4 equals 0, for example. Well, let's take a look at the next slew of definitions. So you'll notice on definition 4, definition 5, we'll do one graph for both of them. There's infinities again. That's kind of weird. We've seen infinities before, but for these two problems, before we get too far of them, it's good to tell the difference between where is your infinity. It makes all of the difference. So let's pause for a moment, and in section 2.2, these were our first limits. We were setting x to go off to infinity. And if it settled down on a function value, we said there must have been an asymptote on the graph there. That's only if x goes off to infinity. Now this time, we're saying that the output is infinity. We've seen that in a couple times, but this time we're really going for this kind of description. So let's do a graph that goes like this. And we'll put in some weird issues over here at -3, 4, 5. Let's go off to -5. Instead of a horizontal asymptote, we're going to put in a vertical asymptote. So if you head towards finite number and you get an infinity, this means there is a vertical asymptote at x equals a. We drew a vertical asymptote, and this dashed line would have equation x equals -5. Well, let's go and put down another one, maybe at 3. Here's another vertical asymptote. And I'll plot the function itself in blue. So one graph for this. Horizontal asymptotes, your graph can cross them. It can cross them many times, infinitely many times potentially. But vertical asymptotes are special. These are honest to goodness barriers to your function. Your function, if it crossed this thing, well, it would also fail the vertical line test. It wouldn't be a function at that point. So when we go to draw this, I'll usually draw it in this kind of way. It's heading up towards a vertical asymptote. I'll use the upper arrow to say it's approaching it arbitrarily close, but we can't let it ever cross it. In fact, it can't even touch the vertical asymptote. The next thing we could do is make it come in this way. I'll let this edge of the curve go down in that way. And let's make it finally go down in that direction and maybe settle off in those directions there. So that's overall one entire graph. And now let's take a look at both of these kinds of limits. This one here and this one here. First, this one says, if the limit as x tends towards a of f of x is positive infinity, that means f of x can be made as large as you want, arbitrarily large. All you have to do is let x be as close to a as you like, but not equal to a. This time you really can't let it be equal to a because that's on a vertical asymptote. By its definition, the function is undefined there. So here we can take, if we're thinking of this portion of the limit as x tends towards -5 for the graph of, or for the function f of x. Well, if we look at this region, I circled this, x equals -5, so we had to say x is tending in that direction towards -5. It's meaning both directions, but the curve is blowing up, heading towards positive infinity. We'll just put infinity right there. Likewise, for this end, the curve is going downwards, so we would write the limit as x tends towards, this one is 3 of f of x. On this end of the curve, it's heading downwards, it's just plummeting, and so we'll use negative infinity to describe that behavior. So those are our two limit values right here. For a positive infinity, you'd expect this kind of graph. For negative infinity, this would be the expectation here. Any questions about that so far? Okay, so next, the fact that we head towards a finite number and got infinity means x equals -5. Same over here, we headed towards a finite number and gotten another infinity. That means x equals 3. Both of these are vertical asymptotes. We could definitely see that from the graph. We started by drawing the vertical asymptotes, but if all you were looking at was this, it's important to know also that implies you are looking at a vertical asymptote just from that information right there. Well, any questions, folks, at the moment with these definitions? Okay, there's definitely a lot to absorb with this kind of material. And one thing that's, again, very, very tricky is there's a lot of symbols right here. I mean, this is a complete English sentence, a proper English sentence. It's saying the limit of the function f of x as x approaches -5 is equal to, there's our verb, infinity. Well, there's so much going on there, sometimes it's easy to kind of lose our way. This one gave us a vertical asymptote, but this one did not. There's no vertical asymptotes right here, even though we got an infinity. Likewise, let me move this over. We got an infinity over here, but no vertical asymptote. So what's missing? They were not heading towards finite numbers. They were going off to a negative infinity on this one. You can't get an asymptote like that. You have to head off towards like 12 or 2. And same problem right here. These were heading towards infinities. If we're not heading towards infinities like on these, if you instead headed towards a finite number like this and got that as an output, automatically there's a vertical asymptote on your graph. Well, that's a lot to absorb. Any questions so far, folks, with those ideas? Okay, let's go off then to this problem right here. Well, we'll try to tie this all together. This will be kind of our group activity. Group activities are a little bit tough when the class is split up, but we do the best we can. Oh, and I should mention, definition 6 is just a reminder about vertical asymptotes. Any one of these would always result in a vertical asymptote, x equals a. And the important thing is you're heading towards a finite number on every single one of them. Some of them are single-sided, like this one, heading towards the left, this one heading towards the right, but those were still going to be honest vertical asymptotes. So here's our big tie together the problem. Example 4. We have one function, this time it's called r, for no apparent reason, maybe it's revenue, who knows. It comes in a whole bunch of different segments, but still just one function. Looks like we have a vertical asymptote at -3, +2, and +5. So we'll deal with those as we run through the questions. And let's say for this first one, how about for people over Zoom? Anyone see the value of this limit here as x tends towards 2?
Would that be infinity?
Negative infinity.
Yeah, good call, folks. And no worries, it's kind of hard with the additional lag dealing with Zoom and multiple people. We might talk over each other. There, we got through it. We might talk over each other here and there, but no worries, we'll always get through it. But yep, absolutely. If we're heading towards 2, we go to 2 on the x-axis. Notice that the curve is plummeting on both sides. That's important because this is a double-sided limit. So yes, this one heads towards negative infinity altogether. Well, that's one down. If we head towards 5, I mean, it's the same kind of thing. At 5, it's going upward, it's blowing up. So we'll say that this one is positive infinity instead. But now they get a little bit funky. When I print these exams out, I actually look at the exams themselves to make sure that prints. Like, make sure there's no issue with the toner and you did get that negative sign, and that portion prints as well. Now we're looking at single-sided limits. We'll start off with this one. We're heading off towards -3. How about for folks in class today? Anyone see the output to this limit? Good call on that one. When it says -3 with the negative sign to the left, that means we're going this way. We're staying to the left of -3 the entire time, but we're definitely going downwards. We're plummeting, so negative infinity like you mentioned. How about for folks in Zoom? Anyone see the limit if we head towards -3, but from the right?
Infinity?
Absolutely, good call. From the right, the picture looks like this. We're getting that as a response, or that as the outputs rather. They get larger and larger the closer you get to -3. So that's the end behavior on that end of the curve, or that end of -3 for the curve. Well, we got it, folks. That's all the limits. Now, for the vertical asymptotes, we just look at this information. If you output in an infinity, and you're heading towards a finite number, you've got a vertical asymptote, and the vertical asymptote is that finite number. So from here, here, and here, the equations of the vertical asymptotes go x equals 2, x equals 5, x equals, oh, not quite 3, but -3 rather. So it doesn't matter if it's in 2 different directions, we would just write the one equation there. Well, we did it, folks. That's the rundown of limits that output values at infinity. Now, here's one thing that's a little bit technical about these notes, and it actually does make a difference, unfortunately. Let's say it's right here. Lim x goes to a, so just generically, f of x equals infinity. Whenever we see this, we feel like the limit existed, but in actuality, this limit does not exist. By stating the infinity, we're just saying the reason it doesn't exist. The function is blowing up towards infinity. If we put in negative infinity, that one doesn't exist either, and we're just giving a little bit information as to why it doesn't exist. Here at negative infinity, it was going downwards. So the limit doesn't exist. This just says, or this specifies the way it doesn't exist. The type of failure that we have in that limit, in other words. So that's really kind of a technical issue right here. Like I mentioned, it's a problem for us because it really does actually matter. Let me go to one portion of the notes. We'll see this again in section 2.4, but from the Moodle website, let me go back to these guys, the good old limit laws. We're going to restate them. They'll look almost the same, except it'll be the limit as x tends towards a. Same kind of laws. But one of the things that it specifies, and it's required, is this limit as x tends towards infinity of f of x, and this one as x tends to infinity of g of x, they both have to exist, which means you're not outputting infinities on those. This one might equal 5, this one might equal 4, but never an infinity. If these limits output an infinity, none of the limit laws are guaranteed to work any longer. So in other words, back to this limit does not exist. The infinity is the reason why, and here's the bigger warning. The limit laws do not apply to this limit because of the infinity right there. Let me actually fix that arrow. Let me point it this way. So that limit, we gave it an answer. Here's why it doesn't exist in infinity. But the bigger takeaway is all of those limit laws, which are fantastic properties, don't apply to these kinds of response or these kinds of outputs with limits. Well, that's a lot of talking, lots of graphs so far. I'm not done with these notes. We still have a good amount to get through, but we'll definitely finish it on our next class meeting. Let me just show you where we're at so far. The next problem is similar to what we've been doing before. We're going to sketch a graph, but this time, this is the information that our graph has to satisfy. In other words, it's backwards from this problem. We had properties for limits we wanted to find, but the graph was provided. The next problem we're going to do might look like this. Here's the properties we want, and we'll produce the graph that satisfies all of them. It is a trickier problem because we're completely inverting the process we've done in most of these examples, but it's an important problem. This one will make it to an exam in some way, probably. It's probably going to be a quiz problem somewhere, somehow. So we'll finish off this one when we come back. And I put a special warning on this one. This will be a problem we look at right before we take a look at the limit laws when x tends towards a finite number. And here we're seeing what happens to the function values as we attempt to approach 2 on that rational function. But the warning is, this is a problem we won't do a lot. Its whole purpose is to segue into section 2.4, where we'll begin to use the limit laws. Well, that's where we're at so far. And, well, let's see, we've got about 7 minutes. I'll leave it up to the class today. We can attempt example 5 or take a look at it when we come back. Any volunteers in class or in Zoom on what we should do next? Let's go with that. My worry about this one is there's a lot we have to produce on our graph and it's a little bit tricky. We could do it in 7 minutes, but let's reconvene on, let's see, this is a Monday. Let's reconvene next Monday and we'll start right here on example 5. That means if you'd like, you can get started early on section 2.3 in WebAssign, but there'll be a couple questions where we just haven't gotten that far. So keep that in mind as you work those problems. Well, any last questions for the day then, folks, before we call it a night? Oh yeah, go ahead.
Clarify, it's the first exam next week.
Oh no, I think we still have a good amount of time until that one. It's going to be on Monday, February 5th. Thanks for mentioning that. I also forgot an announcement myself because you mentioned that. I did email everyone in the class. So if you're registered for this section, I'm assuming you're probably taking the exam in person in class on the day of the exam. If there's a reason that that might not work out, just get in contact with me and we'll make it work some way, somehow. If you're registered for section 11, then I'm assuming you're probably taking your exam on the Pocatello campus testing center. I'll initiate contact with them, send a roster, instructions, things like that, and then they will reach out to you. But I'll give a lot of reminders as we're getting closer to our first exam where we're figuring out how all this stuff works. So thanks for mentioning that. Did that answer your question though? Gotcha. Other questions so far? Okay, well, have a great night, folks. I know it's just Wednesday, but have a great weekend. It's a weekend as far as this class is concerned. And when we come back, we'll be right finishing off 2.3, segueing into 2.4 next Monday.
Thank you.
Yep, have a good one.
Thanks.
You bet.